So I thank the organizers for inviting me to speak in front of this audience. I start with a disclaimer. This is probably categorized in the general announcement of the conference as one of those interdisciplinary physics talks. So don't expect anything too familiar, especially if your main interest, like I assume, is out of equilibrium physics. So I had the immense privilege of both interacting and even collaborating with both Claude Dixon and Cyrano de Dominicis in a smaller sense, because we only committed a comment, not really a paper. But I could really see these two people at work in great detail. And I think Roger was perfectly right when he compared their ways of calculating. Claude always looking for the kind of least resistance path, and Cyrano going straight through the north face. But what's remarkable between these two, if you go beyond these two very different approaches, there's a detail which always struck me, is that no matter how difficult, no matter how formidable the calculations were, in both cases, they were writing these handwritten notes which were extremely neat and clean. I've never seen such a thing. You know, when you compare like the probability of making mistakes and things like that, and when you look at those notes, it's amazing. Okay? So that's one thing I just wanted to say. So now for something completely different. I'm going to discuss some equilibrium problem, which is at the boundary between physics and combinatorics. Okay? So some of the methods I will employ here are brought from combinatorics, and I will try to explain the kind of systems we're looking at. So this is a collaboration essentially with Mathieu Lapa at Urbana-Champaign in physics and Emmanuel Guiter here in Saclay. Okay, so this is the plan. I will introduce the kind of problems I'm looking at, the tangent method, which is essentially the method we are going to probe throughout this talk. And so the type of problems are essentially tiling problems of domains of the plane. Okay, so we're two-dimensional, first thing. And I will use a sort of emblematic case, which is the domino tilings of the Aztek Diamond, to show how the method works, and then show how you can apply it in some more subtle cases in which you have a whole range of results. Okay, and then if I have time, I will show also how it could expand, how it extends to alternating side matrices. Okay, so here is the type of combinatorial problem. So tiling the finite domains of a plane with finite sets of tiles. Okay, so here are the two main examples, the domino tiling. So you have 2x1, 1x2 dominoes, and you have a portion of square lattice that you want to tile. And so this is this Aztek Diamond. Okay, so it's a square, but it's cut in a fancy way in your square lattice. Okay, and then rhombus tiling, just the three adjacent triangles you can form on a regular triangular lattice, and they form three types of tiles, right? And you want to tile certain domains. And we're going to look at the problem of spatial boundaries, that is fixed completely one boundary, and see the effect on the thermodynamics. So all these problems I'm showing here can actually be rephrased in terms of NILP, non-intersecting lattice paths. Okay? And so there is a well-defined way from the tiling configuration to go to some non-intersecting path configurations, which essentially join some boundary to one of the other boundaries. And the gas of such non-intersecting paths is, of course, the interesting problem. And the interaction, this non-intersection, this fermionic interaction, is responsible for all sorts of very nice things happening. So just because I don't have time to do the whole history of the subject, but these are also dimer models. Okay, and you know that the literature about dimers is enormous. There's all sorts of methods which have been employed, some very standard ones like the Castellane matrix and stuff like that. more modern methods have been employed, like asymptotic representation theory. So most of those methods are probing the bulk of the systems. So the method I want to show today was devised by Andrea Sportiello and Filippo Colombo 2 years ago. And it's kind of a revolution, I think, because instead of probing the bulk, it only probes the boundaries. Okay, and so I'll try to show how this thing, and of course it simplifies enormously the problem. Okay, so what are we looking for? We are looking for the appearance of different phases, essentially ordered and disordered phases, which I can call crystal and liquid. So what does a crystal look like in domino tiling? Something like this, like a brick wall. Now in path formulations, it's regions in which paths are very regular, very parallel to each other. Okay, so at large size, now you have to scale things. You will find a sharp separations between these two phases, and that separation will be along some curve, which is called the Arctic curve for obvious reasons. Okay, so here is how we are going to attack the problem by enumerating configurations, right? So we have to reformulate all the problems we look at in terms of these non-intersecting lattice paths. Then, once you have rephrased things in terms of non-intersecting paths, basically your partition function is something like the partition function for configurations of non-intersecting paths with fixed beginnings and ends. Okay? So you have fixed starting points for your paths, fixed ending points for your paths, and the partition function is well known to be a determinant, and it's just the determinant of the partition function of a single path now on the same structure, but going from the ith starting point to the jth starting point. So you form a matrix, right, with indices ij, and then the determinant of this matrix computes this. So there's many ways of understanding this, but in combinatorics they call it the Gessel-Vienno-Lindström determinant. But we, as physicists, we know that this is just the weak theorem for lattice fermions. Okay, anyway, of course the partition function, you can put paths if you want, or just enumerate things. Okay, so now here is the interesting thing that you can do is, so you're going to have some explicit matrix here of which you want to compute and estimate the determinants in large size. And there is a very powerful way of computing the determinant, which is just the Gauss method, right? So in more fancy terms, it's called the LU decomposition. So you have a matrix, right? And you want to write it as the product of a lower times an upper triangular matrix. Okay, and the lower, you make it even uni-lower triangular, meaning with ones on the diagonal, right? And then, well, you're going to read here on the diagonal of U exactly what you need to get your determinant. Okay, so we are going to use this in an essential way. Okay, so now I want to describe the tangent method of Colombo and Sportiello. So imagine you have this situation. You have these starting points which are fixed, ending points which are fixed. Now you have these non-intersecting lattice paths, so they have to be inside a certain domain, right? And you're looking at what happens in large size. So what you expect is that you see the beginnings of the paths, they don't have much place to go, so it's going to always begin with some frozen regions, right? And presumably it will end also with some frozen regions. And entropy of the configurations will be in the middle. So I expect some curve that separates the frozen regions around the boundary from the liquid regions in the middle. Think of a freezing lake. Okay, so all right. So what's the method? The method consists in, so this we understand we can compute as determinant of a certain matrix. So the idea is the following. It's to just modify slightly the setting in which you see this last path in the thermodynamic limit is going to actually tell you what the shape of this curve is, at least the top portion of the curve. So you want to understand this last path much better. So what you do is you move its end, okay, so just away from the domain. So no matter where, here I do it along this line, but I don't have to. And now we have this situation. So here, things have hardly changed, right? It's still the same situation with one less, but n is very large. But what we have here is a path which is going to interact with those guys before it just takes off. Okay? And the idea is that once it takes off, it doesn't feel the presence of the other paths, therefore it most likely will follow a line, right? So if you can figure out the position x of the most likely exit of this path from the domain, well, this will fix a certain line, which is parameterized by the position E prime that you fixed wherever you wanted. And so you'll have a parametric family of lines which are tangent to the Arctic curve. So if you take the envelope of this family, you will recover the Arctic curve. So that's the idea. So let's see how it works. Okay, so this relies on two properties. So the first property is this straight line when you are away from the other paths, right? So left to its own device is a directed random path with fixed endpoints is more likely to follow a straight line. Okay, fine. And that can be proved. That's rather easy. The second point, which is a bit more tricky, is that the line followed by the external path away from the others is tangent to the Arctic curve. Okay, it's reasonable, but it still would have to be proved in general. Okay. All right, so let me show you how to apply the tangent method now by computing partition functions. Okay, so what you have to do now is to compute the escaping path partition function. Well, I call it ZNL. I just generically call L like the displacement of the exit point from the original endpoint. Okay, so you have a certain partition function ZNL. Okay, and you can form a one-point function by dividing it with the original partition function in which the displacement was 0, right? And then you have a second piece, which is what happens after you exit the domain, right? And there it's very simple. In general, it's just a single path with certain rules on this lattice, which goes from the exit point to the end point that I have moved away. Now, the scale estimate has to be done on this sum, right? I sum over the exit path positions over this L of the product of these two quantities. I do some reasonable scaling. Everybody scales with n, the number of points, the size of my system. And I have here, I parameterize my exit points by a number a, which will be a free parameter, which will be the parameter for the parametric family of tangents. Okay, so then I just do some asymptotic analysis, and by saddle point, I'm supposed to find this most likely exit point, and the tangent line will be recovered, and the Arctic curve as the envelope. Okay? So the main thing is what we have to do is really to estimate those two guys. So this one is easy, but this one is difficult. This one-point function at large n. So here is a way of doing it which costs very little somehow, right? So this partition function, as we said, will be the determinant of some relatively nice matrix, okay, of integers if I don't put any energy in my problem. And the one with displaced endpoint for one of the paths is actually very close. If you remember this Gessel-Vienno formula, it's this Aij is just the partition function for a single path from the ith starting point to the jth endpoint. Now, whenever j is less than n, I haven't changed my endpoint, so the matrix remains the same. The only endpoint I have changed is the last one. So it's when j equals n, so the ain now, is a new partition function. Okay? So, in fact, what happens is that in my matrix, I have only changed the last column. And that's very important. So if you realize that, then you do the LU decomposition that leads to the partition function, right? So you find L and U. The determinant is given by that of U. But now if you apply L inverse on the left, of course, L inverse A is U. But you take the same L inverse and apply it to A tilde, the guy with modified last column, then U tilde is also going to be upper triangular. So by just the standard basic L matrix, you're going to get the already modified problem solution. Okay? And so then my one-point function is just the ratio of these two determinants, and as the two matrices only differ in their last column, the two U matrix elements that are relevant are just the two last ones. So it's even a ratio of two matrix elements. So it's a very, very simple quantity. Okay, so you just have to estimate this guy and then do your scaling. All right, so let me turn to some concrete example here. So this is called the Aztek Diamond. So you see the size will be essentially the number of steps you have along each of the 4 sides here. So it's a domain of a square lattice, right, which is tileable by 1 by 2 dominoes. Okay. So here is a picture of a very large random configuration. And as you can see here, you have 4 regions which are in blue, red, yellow, and green, which correspond to frozen regions induced by the corners, right? So in a corner, things have a tendency to be looking like a brick wall. Now there's 4 colors because the top and bottom are different. If you start bicoloring your lattice, you will see that essentially the top dominoes and the bottom dominoes are not the same. Okay? So, but what's interesting here is that there's a formulation in terms of non-intersecting so-called Schroeder path, large Schroeder paths. So the Schroeder paths are paths on the square lattice, so vertices of a square lattice, which can go in the direction 1, 1, right, up by 1 and right by 1, or go straight by 2, or go down by 1. Okay, so along diagonals of squares. All right. So here I just represented the bijection. As you can see, there are 2 types of horizontal dominoes, and when it's pink, it's crossed by a line, and when it's blue, it's empty. And there are 2 types of vertical dominoes, and when it's purple, it's crossed by an ascending path, and when it's green, it's crossed by a descending path. Okay, so you have a bijection. So now you can forget everything about the tiling model and concentrate on lattice paths. Okay, so this is the artist's view of a very large number of such paths, right? And of how to apply the tangent method. Okay, so we have these 2 partition functions we want to calculate. The top piece here is just single path from B to C. And the bottom here is, again, a non-intersecting lattice path configuration, of which the first, the top one, ends up at B instead of ending up along this line. Okay, so we have everything we have to compute. Now, the computation turns out to be extremely simple in this case. So it's best seen by using generating functions. You see, the matrix Aij from the ith path to from the ith starting point to the jth starting point, that is going from here to there somewhere, right, and going up, down, or straight, is given by this generating function. So it's the coefficient of ziwj in the power expansion of 1 over this. And you see z corresponds to going up, w going down, and zw going straight by 2 steps. So you find this number. And the LU decomposition is really child's play once you have realized that your generating function is this. You just realize that the convolution of these 2 rational functions is exactly this rational function. Okay? So it's a one-line proof that LU is equal to A. Because taking the product of 2 infinite matrices amounts to taking the convolution of their generating functions. Okay, and explicitly you see these are nice combinatorial numbers. Okay, so the partition function in particular is just the diagonal elements, the product of diagonal elements of the upper triangular part here, and that's just the power of 2, as is the standard, now a very famous enumeration result. Okay, so let's go now to the modified partition function, in which you have an exit point at position L. Then your matrix changes in its last column, not very much. Okay, there's a slight change. The U tilde result of L inverse on A tilde is given by such a form, and you can compute it explicitly, and you find this explicit formula here in terms of binomial coefficients. I skip the proof. This is the other piece, the piece with where the free single path goes from the exit point to the arrival point that you fixed by hand, and it's again expressed simply in terms of matrix elements of A. And in the end, you just have to do this asymptotic evaluation. So you just evaluate these actions by using Stirling formula, essentially. And as you can see here in this calculation, there was an upper bound here given by the position of the exit path. So it means that in this asymptotic expression, the integration variable psi is saturated by this position psi. Okay, so clearly S1 being this, you see that the critical point is phi equals 1/2, and so it depends on whether psi is larger or smaller than 1/2. Okay, so you have these two cases. You compute things, it takes a little while, and you find eventually that the solution for the most likely exit point is given in terms of a parametric position of points that you have moved away by a very simple relation like this. Then you get the equation of your family of tangents. So y and x are the coordinates in the plane, right? And z is this parameter, and you see this is completely explicit. Then the envelope of the family of lines is just expressed by saying that the line, you're on the line, and that the derivative with respect to the parameter of the line are also 0, and you end up with the circle. So this is this Arctic circle. That's why the whole thing is called Arctic circle. It's because of this Aztek Diamond example. So if you compare this derivation with the standard one that people used historically to find the Arctic circle, it's infinitely simpler. Okay, so I think this is a good advertisement for the method of Sportiello and Colombo. By the way, Sportiello is in the audience, so you can ask him more questions. Okay, so here is the second problem I wanted to show you, which is a little bit more involved. So now we are looking at rhombus tiling. So you see there are 3 types of rhombi. I deform things a little bit so that they fit on a square lattice, but that's not a big problem. And essentially what I'm doing is the following. I consider boundaries which are straight here, and then here I have indentations at every point, and here indentations at arbitrary points. So I choose arbitrarily the positions A0, A1 up to AN here, and I decide to have indentations in my domain. Okay, and now I'm tiling this guy. So in terms of lattice paths, it's those paths. These are paths drawn on the square lattice, right, which can go right or down, if you see them going from left to right, and which end up at prescribed positions. Okay? All right, so let's just do the same. Right? So there's an Lindström-Gesell-Vienno matrix here that essentially counts is the partition function of a single path. Okay, actually I start from the bottom and I end up on the left, so my paths are going up and left. Okay, so from the 8th point here, AI, to the jth point here, J, and it's just this combinatorial number. And then the LU decomposition, that's quite remarkable, is completely explicit. So if you compare with what we had before, we had binomial coefficients. This is some sort of deformation of binomial coefficients according to this position A. So now we have an explicit formula for the upper triangular part of A, right? And we just, so of course, if you multiply this by A explicitly, you can rewrite it as a contour integral. And it's very easy to see that this contour integral reduces to its residue at infinity. And the residue at infinity is 0 whenever I is larger than J. So you can see here immediately on this formula that the resulting matrix is upper triangular. So this does the LU decomposition trick. Then so you can even compute the diagonal elements of U explicitly. They're very nice. And so the partition function now becomes the ratio of 2 determinants, right, which are the Vandermonde determinants. One is of the A's, the end positions, and one is of the initial positions, 0, 1 up to n. Okay, so a very simple formula for the partition function. So that was the first step, partition function. Now we look at the partition function with some exit point. Right? So here is now the situation, right? I'm moving the top endpoint to somewhere along the vertical line, and I'm looking now at the bottom portion, which I call ZNL, which is partition function of those guys with an exit point at position L. And the top I call YLR. So same thing as usual. We try to use the LU decomposition to find these asymptotics. Okay. So here is my new matrix, right? It's the old, as long as I'm not in the nth column. But in the nth column, it changes a little bit because now my endpoint, instead of being to the far left, is somewhere in the middle here. Okay, so it changes things a little bit. The one-point function is still the ratio of these entries of my upper triangular matrix in the decomposition of A, which can still be written down as a certain contour integral. And now the contour is a little bit more subtle. It has to encircle only the arrival points here, or starting points actually, which are such that they are larger than L. Okay, so to the right of this vertical line. Okay, so we have an explicit formula here. And y is even simpler, it's just a binomial coefficient. So here is now the asymptotics that we find. So asymptotically, what we are going to assume is that these fixed points I that we have fixed are actually obeying some scaling hypothesis, right? So I'm looking at very large systems in which I fixed not directly the positions AI, but a certain function of I over n, which scaling with n will give me the AI. Okay? So the only thing I have to know about alpha is that it's piecewise differentiable and that its derivative has to be larger or equal to 1 in order for the a's to be strictly different, right? Otherwise, two a's could be equal. Okay, so applying the tangent method with Emmanuel Guiter, we found the following parametric equations for the Arctic curve in terms of, so t is a parameter in R, and x of t is just the exponential generating function for the moments of the distribution of those points. Okay, so you give yourself this distribution of points, which is the boundary, essentially the shape of a boundary. And now in terms of the shape of a boundary, we have the explicit shape of the Arctic curve. So it's kind of a transform from one to the other. Okay, and the proof goes exactly the same way as before, so maybe I shouldn't bother you with details, right? So you find the total action corresponding to the product of these two quantities, and it involves this integral now, right? And you also have a contour integral over this parameter t. So these are the two novel things compared to what we had before. You write the saddle point equations, and you find that everything is rational in terms of x of t. And then you write the equation of a tangent line, and you see x of t directly gives you, very quickly, the slope of a family of tangents. So everything is parameterized by this t now, right? And x over 1 minus x, or x minus 1 over x, is the slope of this family of tangents. And t is actually the intercept with the horizontal axis. Okay, so very simple formulation. The envelope is obtained by just differentiating with respect to t and solving the system, and that gives you the answer. Okay, so very simple answer. So after we did this calculation with Emmanuel, we became aware that some other people had done it using asymptotic representation theory. And it looks really much, much more difficult than what we did here. So I think this should be seen as really a validation of this method by Andrea and Filippo, and should be really quite convincing. Okay, so let me comment a bit more on the problem here, is that there was actually three ways of looking at it, because there are three distinct sets of non-intersecting paths that are in bijection with the same losange tilings, rhombus tilings, okay, as you can see on these pictures. So it means that you could have applied the tangent method in three different ways, okay, with different paths. And remarkably, they all, of course, lead to the same answer. So that's quite nice, with different domains of t of my intercept with the x-axis. So quickly, I give you a few examples. So I recall that alpha of u codes the boundary condition. So here is, for instance, a case which we call the pure case. AI is pi, so it means I have little indentations every p, right, spaced by p along my boundary, my bottom boundary. Okay, so if I have that, the alpha of u is just p times u, so you can compute this exponential generating function of the distribution of those points. It's given by this very simple formula. and you plug that in the formula I gave you for the Arctic curve, you get something like this, which is tangent to the one direction here, and here are the two frozen regions corresponding to lattices made only of those tiles on this side and those tiles on that side. And as you can see, here I go slightly beyond the tangent. Inside the tangent, the paths had to be parallel, so it had to be a frozen region, but it extends slightly beyond. Okay, and what you can show is that for p an integer, then this Arctic curve is actually algebraic of degree 2p minus 2. Okay. Now another case which is interesting is the piecewise linear case. Okay, so now alpha prime is going to be constant, but by pieces. Okay, so constant on certain intervals. So this is the situation. And remember, these constants have to be larger or equal to 1. Okay. So now the x of t has this form. So very nice extension of the previous result. And now the boundary looks like this, and you see between theta I minus 1 and theta I, which correspond to these numbers here, you have a density 1 over pi. Okay. So here are particular cases. So a freezing boundary is a boundary which is going to induce a macroscopic domain inside my system that is frozen. So here is one example. It's when p equals 1. So p equals 1, it means that I have an indentation at every point, right? P was the distance between two consecutive indentations. Okay. So, well, here it speaks by itself. You can see that the paths corresponding to such configuration are frozen in this big triangle. Okay. So this is already one way of inducing freezing on a boundary. Another way is to just have a straight boundary. Okay, so if you have a straight boundary like this, it corresponds to having a big gap now between the A and the next A, right? So macroscopically, this will be a macroscopic domain without any A, right? And you can obtain it from my piecewise linear system by sending P to infinity, with width of the interval times P being finite. Okay, so you get something like this. So microscopically, what it means is that I have a turning point somewhere along this boundary where I go from one type of paths to another type of paths, right? And so this will give rise to a tangency point of my curve, my Arctic curves here. Okay. So here is an example of partially frozen boundaries. So that's domains in which I have p equals 1, so all the indentations. Here p equals 2, so every other point indented and all indentations, and every other point and all indentations. And this is, in blue, the Arctic curve that you get out of this. And I represented the type of tiles that fill the various frozen domains. Okay? So here is another example in which I have now on the sides I have regions with p equal 2, and in the middle what I have is a gap, so p equals infinity. Okay, so now my Arctic curve is made of this external piece plus an inner piece with two cusps. Okay. All right, this is a fully frozen boundary in which I use my two ways of freezing. So one which is p equals 1 and the other which is p equals infinity, and I'll alternate them. And as you can see, it just amounts to tiling a domain which has the shape which follow all those lines. Okay, so you get the Arctic curve in this way. All right, and you can also play with nonlinear cases. All right. So now I want to show you a nice little geometric construction of the result of this theorem I showed you. So x of t is the data, right? You give yourself x of t by fixing whatever you want to happen on the boundary. So you can plot f of x of t. So this is a plot of x of t, the purple lines, right? So then there's a construction. T, remember, was the intercept of a family of tangents with the x-axis. So let me take t here, take the point of coordinates tx of t, right, which is m, project it onto the line x plus y equals 1. Okay, that's this point Q. So the claim is now that the tangent line will be perpendicular to the radius vector, which goes through 0 for the origin and this point, right? And this exactly tells you that the slope of a tangent has to be the slope that I had before. Okay? So this, normally, if I move t around, I will move this point around, I will move this around, and I will move my tangents around. And to show you that this really works, so let's see. Okay. I have a little movie that Emmanuel Guiter made. Okay. All right. So I'm just going along the curve of x of t, and that draws for me the tangent lines. Okay? Want to see it again? Oops. Interesting. I guess you can't see it again. Ah, yes, you can. All right. So that's the tangent method at work. All right. So I'm not sure how much time I have left. I could stop here if it's convenient to everybody.
For a few minutes.
A few minutes. Okay, so I can maybe make comments. Okay, it's here. And now I have to do, where is it? Affichage. Control L. Thank you. But I like this kind of solution. Control L. Thank you. All right. So I just want to add a last comment. That this method, after all, why did they have to come up with such a method? Okay, it simplifies your life drastically. It probably allows to get some new results on cases that are really hard to track. But the main point there is that it seems to extend beyond free fermions. Okay, so non-intersecting lattice paths, the only consideration you have is that they shouldn't cross, right? Now, there are some models, like the 6-vertex models, which can be really understood in terms of interacting fermions, okay? And here is the example of the so-called domain wall boundary condition 6-vertex model. So it's a bit like the picture we saw earlier this morning, except that you force domain walls both in horizontal and vertical directions, okay? So you have the 6-vertex model with the ice configurations, which means that you have always 2 entering and 2 outgoing arrows at each vertex. So there's, by the way, a bijection between those objects and so-called alternating sign matrices, which are just matrices that generalize the permutation matrices by introducing -1s in such a way that a -1 always has a 1 to its right and a 1 to its left and a 1 above and a 1 below. Okay? So these matrices are quite fascinating in themselves. And the question that Sportiello and Colombo tried to, and I think answered, was the asymptotic shape of an alternating sign matrix viewed as related to configurations of the 6-vertex model. For that, you transform the problem into a problem of paths, which are non-intersecting but kissing paths, right? It means they can share a vertex, but they kind of bump into each other and go their own way by staying on the same side, okay? But now, of course, there's an interaction energy whenever you bump into each other like this. So these are no longer free fermions. But still, these are paths, so one can actually play with the same idea, right? And so move an end point away and see what happens and try to compute partition functions. And they did that, and it works. And they get a very interesting result, which is the fact that it's not a circle, right? It's a square. It's on a square. It has to be tangent to the boundaries, right? So it should be close to a circle. No, it's made of 4 pieces of ellipse, which are glued to each other at each tangency point. Okay, so what we did is just extend that with a case of what are called vertically symmetric alternating sign matrices, in which, as you can see here, there's a succession of 1 minus 1, 1 minus 1, 1 minus 1, and everything is symmetric with respect to this column. Okay, and it works as well. So I'm not going to go in detail, but this is the quarter of ellipse that you get, and actually by gluing the 4 quarters, you get the entire Arctic curve. So it works. So this is the most remarkable thing. Why does it work? So there's this feeling that yes, it should work because once your path is away from the others, you lose the interaction, therefore they live their own life, and there should be this tangent story going on. But until when? Until which kind of interaction is this going to work, right? We don't know. So there's many interesting open questions associated to this problem, which I listed here. And another direction which we figured out how to do with Emmanuel since I wrote those slides is that we can Q-deform everything. Okay, so this is to be continued. And these are the two papers this relies on. Thank you.
Thank you. Questions? Comments?
Can you say something about the fluctuation of the...
Okay, so the fluctuation have been studied by these other methods. In that case, you really need the green function, so you need to invert the Castelline matrix, and it's hard work. It's much harder.
Don't you expect that they are universal, like the Tracy-Widom?
Yes, we do. So as usual, it's going to be the Gaussian. You do some saddle point, so it's given essentially by the saddle point. But what happens near the tangency points, like at the ends of those domains, is a bit more subtle. Okay, but yeah, we hope we could do the same. But it's been done already, right, in these other models.
Well, there is a big ongoing debate if the fluctuation...
This is Andreas Portiello, by the way.
There is a big debate ongoing on, well, for the free fermions, the space and, the orthogonal fluctuation are on a scale of exponent 1/3 and the transversal 1/2, as well known, KPZ universality and so on. And there is a debate if it is the same in 6-vertex model out of free fermions or not. And people say yes, people say no. There is something that comes out, sorry, too loud, from the tangent method, but in a version a bit different from the one that Philippe has presented, that points towards 1/3 also in the other models. And it's really, yet again, a simple geometric argument that tells you that if you do the game with two tangents, one going on one side, one on the other side, and you play well with the parameters, there is a parabola hidden there, and the 1/3 comes out geometrically by simple dimensional arguments. So, well, the tangent method has something to say on that, but it's more well hidden.
Other questions? So if not, let's thank Philippe again.